Ever wondered how the digital systems around us, from our smartphones to our laptops, function at their core? The answer lies in the world of digital logic and one of its fundamental building blocks, combinational logic. This type of digital logic design is where the output is determined purely by the current inputs, without any consideration for previous inputs or sequences of events. In simpler terms, the output of a combinational logic circuit depends entirely on the present state of its inputs. There's no memory or feedback mechanism involved. At the heart of combinational logic are logic gates. These are basic building blocks like AND, OR, NOT, NAND, NOR, and XOR gates. Each of these gates performs logical operations on input signals to generate an output. To define the relationship between the inputs and the output in a combinational logic circuit, we use something called a truth table. Each row in this table represents a unique combination of input values and the corresponding output. From these truth tables, we derive mathematical expressions known as Boolean expressions. These expressions describe the logical relationship between the inputs and outputs, representing the logic implemented by the circuit. There's a wide range of circuits that can be designed using combinational logic, from adders that perform the addition of binary numbers, subtractors that carry out binary subtraction, to multiplexers and demultiplexers that direct data lines, encoders, decoders, and comparators. The design process for these circuits involves specifying the desired functionality using truth tables or Boolean expressions. Then, the circuit is implemented using logic gates. One key characteristic of combinational logic circuits is that they don't have any feedback loops, memory elements, or storage capabilities. The output is determined only by the current inputs, with no consideration of past inputs or outputs. Another important aspect is timing. Combinational logic circuits respond instantaneously to changes in input signals. There are no clock signals or sequential elements that introduce delays. So, at its core, combinational logic is about the here and now, with no regard for the past. So what makes up combinational logic? At the heart of combinational logic, we have three key components: logic gates, truth tables, and Boolean expressions. Let's start with logic gates. These are the building blocks of combinational logic circuits. They include the AND, OR, NOT, NAND, NOR, and XOR gates. Each gate performs a specific logical operation on its input signals to produce an output. For instance, an AND gate only outputs a 1 when all its inputs are 1. Next, we have truth tables. These are essentially a map of the relationship between input and output values in a combinational logic circuit. Each row in the truth table corresponds to a unique combination of input values and the resulting output. It's like a cheat sheet for how our logic gates should behave. Then we come to Boolean expressions. These are mathematical expressions derived from the truth tables. They represent the logical relationship between inputs and outputs. In other words, they describe the logic implemented by the combinational circuit. For example, the Boolean expression for an AND gate is AB equals sign Y, where A and B are inputs, and Y is the output. Now, when it comes to practical applications, these components are used to create a range of combinational circuits. From adders and subtractors that perform binary arithmetic, to multiplexers and demultiplexers that direct data flow, each combinational circuit has a specific role to play. Let's not forget the encoders and decoders that convert signals into binary code and vice versa, as well as comparators that compare two binary numbers to determine their relationship. These components, working together, form the backbone of every digital device we use. From your smartphone to the most complex supercomputer, they all rely on the principles of combinational logic to process data and carry out functions. In the next scene, we'll dive into some specific examples of combinational circuits and see how they're designed. These components come together to form the backbone of every digital device we use. Now let's see combinational logic in action. Starting with adders and subtractors, these are the backbone of arithmetic operations in digital systems. An adder is a combinational circuit that performs the addition of binary numbers. It takes two or more binary numbers as input and produces their sum as output. A subtractor, on the other hand, performs the subtraction of binary numbers. Moving on to multiplexers, or MUX for short. These are like the traffic controllers of digital signals. A multiplexer has several input data lines but only one output. It selects one of the inputs based on a selection code and directs it to the output. This allows multiple data signals to share one device or resource, such as a data transmission line, improving efficiency. The opposite of a multiplexer is a demultiplexer, or DMUX. It takes a single input and directs it to one of several output lines, again based on a selection code. This is useful for distributing a data signal to multiple devices or locations. Next up are encoders and decoders. An encoder is a combinational circuit that converts a set of input signals into a binary code. This is handy for simplifying the number of wires needed to transmit signals. A decoder does the reverse. It converts a binary code into a set of output signals. Lastly, we have comparators. These combinational circuits compare two binary numbers to determine their relationship. They can tell us if one number is equal to, greater than, or less than the other. These examples demonstrate the versatility of combinational logic, from simple arithmetic operations to data selection and distribution, to signal encoding and decoding, and even comparison operations. Combinational circuits are the workhorses of digital systems. These circuits illustrate the diverse applications of combinational logic in digital systems. But how do we go about designing these combinational circuits? Well, the design process for combinational circuits is quite methodical. It begins with a clear understanding of the desired functionality. This is typically specified using truth tables or Boolean expressions, which we've already discussed. A truth table is a simple way of outlining all possible combinations of inputs and their corresponding outputs. It's a comprehensive map of all outcomes depending on the inputs. For instance, if we're designing an AND gate, the truth table will show that the output is 1 only when both inputs are 1. Otherwise, the output is 0. After we've got our truth table, we move on to deriving the Boolean expression. This mathematical expression describes the logical relationship between inputs and outputs in a symbolic way. Using the same AND gate example, the Boolean expression would be AB, where A and B are the inputs. Once we have our Boolean expression, we can then implement the circuit using logic gates. This involves selecting the appropriate gates, like AND, OR, NOT, NAND, NOR, and XOR gates, and connecting them in a way that reflects the Boolean expression. Now, one key thing to keep in mind when dealing with combinational logic circuits is their timing. Unlike sequential circuits, which have elements that introduce delays, combinational logic circuits respond immediately to changes in input signals. As soon as an input changes, the output changes too, almost in real time. This immediate response time is due to the absence of any feedback loops, memory elements, or storage capabilities. There's no need to wait for a clock signal or any sequential elements. Everything is based solely on the current inputs. This characteristic of combinational logic circuits is what contributes to the speed and efficiency of our digital devices. They allow for quick computation and decision-making, making our laptops, smartphones, and other digital devices incredibly fast and responsive. This immediate response is what makes our digital devices so fast and responsive. Combinational logic is just one piece of the puzzle. How does it compare to sequential logic? To draw a contrast, let's first understand what sequential logic is. Unlike combinational logic, where outputs are determined solely by current inputs, sequential logic takes into consideration the previous inputs or states. This gives sequential logic a sense of memory, something that is absent in combinational logic. Sequential logic circuits incorporate components like flip-flops and latches, which can hold or remember their state. This ability to store information makes sequential logic essential for designs that require data storage or timing operations. This leads us to an interesting point of difference: the presence of a clock signal. While combinational logic circuits respond immediately to changes in input signals, sequential logic circuits are synchronized with a clock signal. This clock signal determines when a sequential circuit will respond to its inputs, creating a sense of order and sequence in the operation. Now let's talk about the importance of both combinational and sequential logic in digital systems. Combinational logic is like the building block. It's used to perform simple operations like addition, subtraction, and comparison. On the other hand, sequential logic adds complexity and functionality to these operations. It enables the creation of counters, registers, and memory units, forming the backbone of complex digital systems like computers. Think of it like this. If combinational logic is the vocabulary, sequential logic is the grammar. You need both to form meaningful sentences or, in our case, to create functional digital systems. In a nutshell, both combinational and sequential logic have their unique roles and advantages. Combinational logic, with its simplicity and immediate response, is crucial for basic operations. Sequential logic, with its memory and timing capabilities, adds depth and functionality to digital systems. Whether it's combinational or sequential, understanding these forms of logic is key to unlocking the power of digital systems.